We present Orbit Surgical, an open simulation framework for learning surgical augmented dexterity. First, we would like to draw the attention to progress of robotics and autonomous driving with the aid of simulation for synthetic data generation and interaction-based learning. Simulation is an enabling tool to create digital clones of real world, generating large-scale datasets to train and test autonomous systems at scale. Minimally invasive surgeries have progressed from handheld tools to Intuitive Surgical's Da Vinci system, providing master-slave teleoperation control with wide range of robotic arm motion. Augmented dexterity in surgeries holds the potential to decrease surgeons' cognitive load and reduce the learning curve. Research works in the domain of surgical augmented dexterity include pattern cutting, suturing, and needle tracking. However, these efforts heavily rely on access to expensive surgical robotic hardware, and learning robust models may require gathering very large and expensive data sets to be able to generalize to unseen environments. So this results in a high barrier for researchers to make progress in this field. Therefore, the goal of this work is to enable surgical autonomy and learning at scale. Surgical environments are in fact difficult to simulate due to the complicated interactions of rigid and deformable components and restricted arm motions. Our efforts focus on development of a surgical robotic simulator that imitates reality much faster than real time, supports contact-rich physical interaction and high-fidelity rendering to bridge the visual sim-to-real gap, has access to robot learning frameworks, and is able to record human expert data for policy learning and run successfully on physical platforms. We develop a surgically focused simulator based on Orbit, which is a unified and modular framework for robot learning powered by NVIDIA Isaac Sim. Orbit offers a modular design to easily and efficiently create robotic environments. Orbit Surgical extends the capabilities of Orbit Framework to simulate robot-assisted surgery, replicating joint articulation and low-level controllers of physical surgical robot platforms, as well as integrating various digital world sensors running on Isaac Sim. This table shows features of prior state-of-the-art open-source surgical robot simulators. They suffer from issues such as limited rendering capabilities, few available surgical tasks, no native support for deformable materials, and importantly, lack of support for GPUs, which prevents efficient learning. To demonstrate the high learning speed facilitated by Orbit Surgical, we compare the throughputs of recent surgical simulators on environments with similar complexity. LapGym, a state-of-the-art framework for robot-assisted laparoscopic surgery, relies on CPU-based SOFA architecture, which limits efficient training. Sorol Project provides open-source surgical task environments for the dVRK robot. However, it lacks native support for deformable body simulation. The table on the right shows the throughputs result in frames per second on the default environment configuration of each project. A significant acceleration can be achieved by highly parallelization of environments in Orbit Surgical. Orbit Surgical provides task environments inspired by the fundamentals of laparoscopic surgery training curriculum to reflect the technical skills for basic surgical maneuvers. The tasks are categorized into single and dual arm environments to provide a spectrum of training complexities. Each task is provided in a standalone environment for benchmarking. These environments can be used for generating handcrafted trajectories, collecting human expert samples using multiple input peripherals, as well as training policies to facilitate advancements in surgical autonomy. The tasks include reaching to a desired position, lifting small surgical objects with high precision, hand over or regrasp the object with one arm to the other, pick and place, and deformable shunt insertion. Orbit Framework supports access to GPU-based reinforcement learning frameworks, which enables training RL policies to solve surgical subtasks involving rigid and soft objects manipulation in a matter of hours by highly parallelization of environments, which is an order of magnitude more efficient compared to other existing surgical frameworks. The left video shows training almost 4,000 of robots learning to lift a suture needle. The middle video shows a trained model to insert a deformable shunt into a vessel phantom. Although it shows proof of concept RL policy to solve a tube insertion task, more work can be explored into minimizing deformation or applied force on the tube body. The right video shows the inference of an RL policy trained only in simulation for grasping and lifting a surgical needle on a real dVRK robot, which shows the transferability for real-world policy deployment. Recording offline training data can help to investigate learning for challenging and long-horizon surgical tasks that are hard to solve by the current RL algorithms. Different input devices, including the dVRK Master Tool Manipulator, can be connected to the simulator and provide input commands and control the robot in the Cartesian space. The video in the middle shows a trained model on a pre-recorded dataset successfully lifting a surgical needle. To show the performance of models trained in simulation, in one experiment, different number of demonstrations were collected for a needle lift task. And from the right plot, we can see that the success rates were improved for the models, which were trained on demonstrations with both randomized initial and goal states. Realistic simulators and synthetic datasets can help with augmenting real datasets and providing pixel-accurate semantic segmentation masks for surgical tool detection, which is a very tedious task from real surgical videos. To show the proof-of-concept workflow for surgical needle segmentation, 2,900 simulation image mask pairs were mixed with different quantities of maximum 100 real needle images. In this experiment, the evaluation metric is IOU, or intersection over union metric, to compare how close the predicted masks are to the ground truth masks on a separate evaluation set of real needles. As the table shows, the models only trained on very small number of real needles performed poorly on unseen evaluation dataset. Combining both sim and real data result in predicting masks that cover most of the needle area, leading to higher IOU value than training exclusively on simulation or real needles. As a result, surgical simulators with high-fidelity rendering alleviates the need for large and expensive real-world datasets for training surgical tool detection models. In summary, Orbit Surgical is intended to serve as a resource on supervised autonomy for robot-assisted surgery. For supplementary materials, please visit our website at orbit-surgical.github.io.